Okay, now we're going to talk about predicting favored reaction directions among pairs of, or between pairs of conjugate acids and bases, given similar or equal initial concentrations, and that shift is as the reaction proceeds towards equilibrium. So, given two generic conjugate acid-base pairs, acid 1, HA1, and its conjugate base, A1-. Of course, A1- forms from conjugate acid HA1 donating a proton to something. It would have to donate its proton to conjugate base 2, A2-. So, in other words, the conjugate acid is not going to react with its own conjugate base. So, here are some sample numbers for the acids and bases respectively. Conjugate acid A1 has an ionization constant of 4 times 10 to the minus 5. We'll say all of these K values are for a given temperature, say standard temperature. Ka of HA2, acid 2, is 1.25 times 10 to the minus 9. Okay, that indicates right there that acid HA1 is the stronger acid of the two. So we can label that stronger acid, and acid HA2 is the weaker acid. Again, this larger number, by a factor of about 10,000, 4 times 10 to the minus 5, indicates that the numerator, the products of the acid ionizing, is larger than the numerator of acid HA2 ionizing into H plus and A2-. So that's why we label acid HA1 the stronger acid. Whatever acid has the higher Ka value, the higher ionization constant, is the stronger acid. To get the Kb values, they don't have to be given actually. The conjugate base of acid HA1 would be A1-. That's just the, after the removal of the H plus, the conjugate base forms. And you know that at standard temperature, the product of Ka and Kb has to be 10 to the minus 14, and that is the case here. 4 times 2.5 is 10, 10 to the minus 5 times 10 to the minus 10 is 10 to the minus 15, 10 times 10 to the minus 15 is 10 to the minus 14. So that all checks out, and the same is the case for HA2 and its conjugate base, A2-. The Ka and the Kb multiply to be 10 to the minus 14. Okay, so here we can actually label the base A2- is the stronger base because it has a greater Kb value. That is, the products of A2- ionizing water will form its conjugate acid HA2 and generate hydroxide, and of course the reactant is in the denominator. Water is not shown. So we'll label conjugate base A1- the weaker base. And then you can just write a reaction between acid HA1 and base A2- to form the conjugate base of acid HA1. We'll label that acid 1 and base 1, which is A1-, and the other product is acid HA2, which is the conjugate acid of base A2-. And it doesn't matter which order you write the reaction. You can start with HA2 and react that with A1-. The only thing that doesn't make sense is that acid HA2 and its conjugate base would somehow form acid HA1 and its conjugate base. So now that we have the relative strengths of these acids and bases, we can just label stronger and stronger, and that forms weaker and weaker. Going back to the given values for determining stronger versus weaker, you won't always be given Ka or Kb values. Sometimes they'll give you the pKa and pKb, so we can approximate what we would have been given just by using our benchmarks from the pH scale exercise. So the Kb of base A1 minus is about 3 times 10 to the minus 10, and you know by the benchmarks that means that the pKb, not using a calculator, of A1 minus would be about 9.5 approximately. Because we know 3 times 10 to the minus 10, it would be almost exactly 9.5. For the Ka value of the acid HA1, we see 4 times 10 to the minus 5, so we can write pKa of HA1. Well, if it were 3 times 10 to the minus 5, the pKa would be 4.5. I'm sorry, 4.5 is right. And if it were 3 times 10 to the minus 5, I think that's what I just said. So I mean 5 times 10 to the minus 5, the pKa would be 4.3. So we're going to call this about 4.4, just between those two. Comparing that to the other acid, the pKa of HA2, well, there we have practically 1 times 10 to the minus 9, so we would just call that about 9.0. Can't really go wrong with that. Could be 8.9. Either way, its pKa value is much greater than the pKa of the other acid, and whatever has a lower pKa value is the stronger acid. Finally, for the Kb, the pKb of acid A2 minus, we have 8 times 10 to the minus 6, which is almost 10 times 10 to the minus 6, which would give a pKb of 5, but we'll call this a little bit higher. Let's say 5.1, not quite 5.2. But we could see that this pKb value of 5.1 is much lower than the pKb of A1 minus. The lower pK value is the stronger substance value. So base A2 minus is the stronger base. So we'll just put a little approximate there. Okay. Over to the reaction. Let's look at what the word stronger means for the acid and the base. The stronger acid means that the acid more quote-unquote easily donates H plus to another substance. More easily means less energy is required for the H plus to break off of the acid that it's currently bonded to. For the base, the stronger base meaning it's better at accepting H pluses than weaker bases. So stronger base has greater attraction for, more easily accepts H plus. The greater attraction means there's a greater potential energy lowering effect. So, by virtue of that, it's not going to be possible that you'll write a reaction that the stronger acid will react with a weaker base. How could it react with a weaker base when a stronger base that has a greater attraction for the H plus that's being donated by the stronger acid is in the same solution? Okay, so in this case, the two substances on the left, the stronger acid and the stronger base, are better, faster at doing their jobs. The acid donating the H plus, the base accepting the H plus, and both of those turning into their conjugates. So given similar initial concentrations or even equal concentrations of both reactants and products, there will be a net shift to the right from the stronger substances to the weaker substances, each forming its weaker conjugate. In terms of kinetics, perhaps the forward rate of reaction is 200 effective collisions per second involving the proton transfer, and the reverse reaction might be 40 effective collisions per second. So there would be a net shift of 160 effective collisions per second. Of course, this wouldn't go on forever. When the reactants are used up significantly and the products' concentrations are greatly increased, then of course both rates would eventually come to equilibrium. So with this game overall, you just look at the pKa and pKb values of each of the substances, or just the Ka and Kb values. You determine which acid and which base is stronger, and then those two substances are going to more quickly form their conjugate weaker acid and weaker base, and that will determine the direction of the shift. Let's try one more example. In this one, we have benzoic acid. We have generic representation HA1. The actual formula for benzoic acid is C6H5COOH. It's an organic acid. Its conjugate base is the benzoate anion, which is benzoic acid minus one of the acidic H+. So that's C6H5COO minus. Methylamine is an organic base. The methyl group is CH3. Amines have N bonded to one or more H's. Most amines are, if they're primary amines, they'll have NH2. So that is the base. Its conjugate acid has one more H+. There's a lone pair on the nitrogen, so that H will bond to the nitrogen. So you definitely don't form CH4, you form CH3 NH3+. And as you can see from the names, anything ending in the word amine will change to ammonium as its conjugate acid. So methylamine turns to methylammonium, ethylamine will turn to ethylammonium, and then you'll see there are conjugate acid naming rules for other types of organic bases that we'll cover later. Okay. I just want to draw these out in a little more detail. Benzoic acid has a benzene ring, which has delocalized pi bonding, and then a bond to carbon, and that carbon is sp2 hybridized, and it's bonded to double bonded to an O, single bonded to another O, and then you have the acidic H. The other H's are non-acidic. They are covalently bonded to carbons on the benzene, or sometimes called phenyl ring. So the benzoate ion would be the anion of that acid after the H+ breaks off from the OH covalent bond. For methylamine, you have N bonded to a methyl group, which is CHHH, an sp3 hybridized carbon, and the nitrogen is also sp3 hybridized. It's bonded to the carbon. It has a lone pair of electrons and two more bonds to H's. So the electron arrangement around N is tetrahedral, but it's trigonal pyramidal molecular geometry about the N. So this lone pair of electrons on the N will attract NH+ from some acid, and thus a covalent bond will be formed, and you'll form N I'm trying to draw that a little bit tetrahedrally. NH3, CH3, and there's a net positive charge because a neutral molecule just gained a proton, an H plus ion. Okay. Here are some established acid and base ionization constant values at standard temperature. For benzoic acid, 6.5 times 10 to the minus 5. For methylammonium cation, 2.3 times 10 to the minus 11. So the benzoic acid is 1,000,000 times stronger acid. So we label that as such: stronger acid, weaker acid. For the conjugate bases, naturally we expect that the stronger the acid, the weaker the conjugate base. So the benzoate anion versus the methylamine base. Here we don't really have A2 minus because methylamine is a neutral molecule, but we're just labeling that as a common base. 4.4 times 10 to the minus 4 is the much more ionizing stronger base, much more reacting with water. And the benzoate anion is the weaker base. Again, we may have been given the pK values, so let's see what kind of pK values we can approximate here. The pKa of benzoic acid, HA1, we have about 7 times 10 to the minus 5. So remember, 7 translates to a 2, so that would be about 4.2. The pKa of the other acid, pKa HA2, there we have 2 times 10 to the minus 11. If we had 3 times 10 to the minus 11, we know we'd be at 10.5. We'll call that about 10.6. So acid HA1 has the much lower pKa by 6 units, so that means it's 1,000,000 times stronger acid. For the base, here we have almost 1 times 10 to the minus 10, so that would give a Kb of A1 minus of almost 10. It's a little bit higher number, so we'll call this 9.9. Could be 9.8. And that's a P there. For pKb of A2 minus, sometimes we'll be calling that BH plus because we are looking at a cation and it looks more like that. Or even better, we'll write the actual formula, pKb of CH3NH3 plus, but this is just to save time. Here we have almost 5 times 10 to the minus 4, which would be 3.3. It's a little bit higher, so we'll call this about 3.4. Because if it were 3 times 10 to the minus 4, we'd have 3.5, and if it were 5 times 10 to the minus 4, it would be 3.3, based on our benchmarks. Either way, we have a base here with a pKb of 3.4 compared to 9.9, so this base is 1,000,000 times stronger. So, let's go to the actual reaction here. Again, writing the acid of one substance reacting with the base of the other substance and vice versa. And going with our labels here, we have benzoic acid, the stronger acid, and methylamine we know is going to be the stronger base. We can look over here to confirm it. It is stronger base, weaker acid. The weaker acid is the cation, the conjugate acid of the stronger base, and the weaker base is the benzoate anion. So again, if we started with similar or equal concentrations, The forward reaction would initially be much faster than the reverse, or somewhat faster. So let's say this is 177 effective collisions per second initially, and the reverse is 11 effective collisions per second initially. That would cause a shift towards the products, as written here. As this reaction proceeds towards equilibrium. We'll look at one more quick example with this B notation for a base. I'll show you a real base. Let's take methylamine again, and then a similar organic base, ethylamine, CH3CH2 NH2. The conjugate acid of methylamine will be methylammonium cation, CH3NH3+, and the conjugate acid of ethylamine will be ethylammonium cation. For whatever reason, people generally have a lot of trouble getting the conjugate acid of an organic base. I really don't know why. So if I label methylamine base B1, what's the difference between methylamine and methylammonium cation, its conjugate acid, is that there's an extra H plus on there. So this would be represented as BH plus 1. And for ethylamine, we could call that B2, and we'll call ethylammonium B2H+. 2 not representing like two of them, it's just the second base. We'll use the standard temperature pK values from the last problem. Here, the pKb of B1 was 3.4, and the pKa of its conjugate acid has to add up to 14 for the pKb. So BH plus 1, that's going to be 10.6. Let's say for ethylamine, or base B2, the pKb2 value is 5.1. That means ethylammonium would have a pKa value. B2H plus represents an acid, so it's really a pKa value, would have to be 8.9. So remember, with P values, the lower the value, the stronger the substance. So as far as the bases are concerned, 3.4 is lower than 5.1 for the pK values. So methylamine would be the stronger base. And as far as the acid values, we have 8.9 versus 10.6. Ethylammonium would be the stronger acid. And then ethylamine is the weaker base, weaker organic base. And methylammonium is the weaker acid. So if I wanted to write the two weak substances on the left-hand side, I could do so. CH3NH3+, methylammonium reacts with ethylamine to form methylamine and ethylammonium cation. And we've predetermined that we have stronger acid and stronger base on the right, and we have weaker base and weaker acid on the left. Thus, given similar or equal concentrations of all four substances at the beginning, there would be a shift from the substances that are better at donating and accepting H+ to the conjugates that they form as a result of the reaction.